Hi everyone, welcome to video 18-1. We're going to be working on finding the volume of prisms and cylinders in this video. So for both of those, you guys, the formula that you're going to be working with is just area of the base times the height. So this is why we did the area formulas first in our last little mini unit. When we're talking about volume, area of the base, and you can see the big B here, this is not little b like when we were doing base times height for parallelogram area. This is area of the whole entire base shape times the height. So it's important that into that spot for B, we could put several different formulas here in this section. For a prism here, first for explain 1, we're going to take the area of the base times the height, and it could be that that's a cube, it could be that that's a prism, which is just kind of like a box shape. But basically, we have a couple of different ways of looking at that. We have volume is length times width times height if we have a prism, and volume is s cubed if we have a cube, because all of the length, the width, and the height are the same. On the next page, we just have some examples to talk through here. So for example 1 part A, we have a shark and a ray tank at the aquarium, and we have some dimensions given for it. And what we're being asked to do is to estimate the volume of water here in gallons. And so all we're going to do is just multiply those three dimensions together. So we have length times width times height, 120 times 60 times 80, and we get 57,600 feet cubed. After we go ahead and multiply that out, now we're going to talk about estimating, okay, well, what does that mean as far as in gallons? So step 2, we're given a conversion factor that 1 gallon equals 0.134 feet cubed. And the question is, do I need gallons on the top or feet cubed on the top? Well, I need gallons on the top because that's where I'm headed, and feet cubed on the top because that's going to cancel with the feet cubed that I already have. So here's my 57,600 feet cubed times 1 gallon over 0.134 feet cubed. So essentially we're dividing by that 0.134, and we're going to get 429,851 gallons. So that is going to be the volume of water in gallons. And then we just do one other conversion factor there, and they're estimating basically, okay, so if we had a tank like that, kind of like at the New England Aquarium, I don't know if you guys have ever been there, but they have a touch tank for the rays. Talk about how much would an architect making the building have to support as far as weight goes. Well, if we have 429,851 gallons, and we know that each gallon weighs 0.833 pounds here in step 3, we're going to use that conversion factor, only notice how we're going to flip that conversion factor because we already have gallons. We want pounds, so we're going to put pounds in the numerator, and that way gallons in the denominator is going to cancel right out for us. So 429,851, we're going to multiply that by 8.33, and we have that a tank this size, which is, I mean, it's pretty big, but not essentially, something that would be out of reach of a tank in an aquarium, but it's 3,580,659 pounds. That's an important kind of piece of information to have if you're the architect or the engineer designing this building where this tank is going to be, or the structure outside where the tank is going to be. So that's how we're going to work through those basic volume calculations, but then also maybe some conversions along the way. So same idea there, guys, as we get to chemistry. Our example here talks about ice versus water inside this cube. And so this cubic container is filled to the brim with ice. We're going to estimate the volume of the water once the ice melts. So let's fill in some values here. Step 1 says find the volume of the cube of ice. We're going to take the side length cubed, or 3 cubed, which is just going to be 27 centimeters cubed. Then you guys, we're going to convert that to mass using first off our density of ice. So Our density of ice back there is 0.9167 grams per cubic centimeter. I already have my answer in cubic centimeters, so I'm just going to multiply by 0.9167, 27 cubic centimeters times 0.9167, and notice my centimeters cubed is going to cancel out with the units in the denominator, and I should have approximately 24.8 grams. Then the question is, we want to estimate how much water is left once the ice melts. Well, 24.8 is the mass of the ice all melted down. It's the mass does not change, obviously. So we're going to use that conversion factor, that once we have the mass of the water, we're going to find the volume of the water. So we're going to use the conversion factor, and that is 1 centimeter cubed per gram. And then once we go ahead and do that multiplication, because we're going to have grams down in the denominator, and 1 cubic centimeter is 1 gram, notice my units canceling out, and times 1 doesn't really change anything. So where we had 24.8 grams, we also have 24.8 cubic centimeters. On the next page, you guys have a couple of your turn videos. So this one's pretty straightforward. These two problems, it says find the volume of the figure, and so basically you see what 1 cube is going to be, and then you just go ahead and count up how many of them there are, and then do a quick multiplication. Same thing here for number 5, only this time they give you that the side has a side length of 2K. So first I would go ahead and make sure that you find the volume of one of those cubes by taking 2K and cubing it, and then go ahead and multiply by how many are in the T shape there. Make sure you do those problems before you move on to Explain 2. But in Explain 2, we're going to be moving on to find not just the volume of a prism, but the volume of a cylinder. So we're using the same exact idea. Want you to get to see that what we have here in Explain 2, and these first couple diagrams are, you can see a new vocabulary word, oblique. If you have an oblique prism or an oblique cylinder, basically that's just meaning that it is it says one non-rectangular lateral face. But I think a better definition is pretty straightforward by looking at the diagrams. It's just basically a cylinder or a prism where you are taking the structure and basically like slanting it to the side, okay? What we need to know though is that the solids would have the same exact volume so long as they have the same cross-sectional area. So they've shaded in that cross-sectional area here. Oops, hold on. They've shaded in the cross-sectional area, and notice it's still the same rectangle, and also that the heights of the structures are the same as well. So slanted or completely perpendicular to the surface it's sitting on, it doesn't matter. And the way that you can think of that is almost like a deck of cards. If you take a deck of cards and you take your hand on the top and just kind of like slide it over to the side, you're going to get a slanted structure. But as far as what makes up that deck of cards, you haven't added any cards to it, you haven't taken any away. It's the same exact amount of cards that's there. So this is what we call Cavalieri's principle, and all we need to know is same exact principle applies. It is still volume equals the area of the base times the height, okay? So once we get to example 2, this area of the base times the height idea gets modified a tiny little bit, because the area of the base for a cylinder is the area of a circle times the height. So we can see and modify our formula when it's a cylinder to be volume equals pi r squared, which we know is the area of the base, the big B, times the height. So let's look at a couple of examples keeping that in mind. Example A, the height of this oblique cylinder is 3 times that of its radius. So we're being told here that this height, and remember height is still at a perpendicular angle, at a 90-degree angle, but this height we don't know that's its exact measure, but we do know that it is 3 times the radius. So let's see if we can figure out what the radius is from some other information. And it looks like we can, because we are told that the area of the base in the diagram is 81 pi. So a quick little calculation there says if we use the area of the base to find r, then that means the area of the base, which is a circle, pi r squared, equals 81 pi. And so pretty quickly, if we take our pi's out of the picture and we do a square root, we get that the radius is 9. So I'm going to draw that on the diagram. The radius is 9. Guys, that makes the height equal to 27. And once we have the height, you guys, we're just going to go ahead and calculate the volume because we already have the area of the base being 81 pi, and we have the area of the base times the height, that is the formula for volume, so 81 pi times the 27 that we just calculated, and we get 6870.7 rounded to the nearest tenth, which is what we were told to do. So the volume is 6,870.7 cubic centimeters. So again, that's just an oblique cylinder. It doesn't matter if it's slanted, we just still need to know its height drawn down to a perpendicular. Let's move on to part B. Part B there says, okay, now we're going to take a oblique prism, which again, doesn't really matter what we do as far as oblique versus completely straight up and down perpendicular. We still have the area of the base times the height formula. So looking through this, we have the height of this oblique square-based prism is 4 times, instead of 3 times in part A, 4 times that of the side length of the base. So what is the volume of this prism? Notice we're being told that the area of the base is 75. So let's figure some things out. If we have the height is 4 times the side length, where S is the length of the square base, then we're going to use the area of the base to first of all find S, the side length. So S squared, since it is a square that we're finding the area of on the base there, side times side squared there, is going to go ahead and give us 75 from the diagram. And then, of course, S is the square root of 75 as we're finding one side length. Now we've been told that H equals 4 times S, so H equals 4 times what we just found S to be, which is the square root of 75. And then now that we have the height, we can calculate the volume. So we're going to take 75, which is the area of the base, times the height, which is 4 times square root of 75, and we're going to get the volume is going to be 2,598, sorry, it's hard to write in the box there, 0.1, and this is cubic centimeters. So now we have some your turn problems, and again you see an oblique cylinder and an oblique prism. I just want you to go ahead and find those volumes as we move on to the next part of the video. Finally, the last part of the video here is finding what we call a composite figure's volume. And so a composite figure, you guys, you can see in the explanation here, is just made up of simple shapes that combine, and it could be that those shapes are added together, it could be that one is subtracted from another kind of thing, but it creates a more complex shape. In the next few videos, as we go through the next sections 18.2, 3, and 4 for this module, we're actually going to separate the composite figure out into a separate video for you guys, because I've known in the past that that's part of what makes these volume problems so challenging for students, so I wanted to separate them out for you. But for this first video, it should be pretty straightforward, so we're going to work through these together. What basically we're going to do is we're going to find the volume of each separate figure and then add the volumes together, in this case for part A, to find the volume of the composite figure. Most of the time you're going to add the volumes together in these examples. We're also going to do in the reflect on the next page, where you can see we are going to do a drilling out or a hollowing out type of thing, and that strategy is a little different. But first, example 3. Find the volume of the composite figure, which is an oblique cylinder on a cubic base, and we're going to round that to the nearest tenth. So first thing we're going to do is find, using the fact that the cylinder touches each side of the cube there, the base area of the cylinder is given to us as 25 pi feet squared, and the reason is because this radius up here translates down to this radius down here. So 5 squared pi is the area of the circle. So we're going to have 25 pi as the area of big B. Then we're also going to figure out some other dimensions. It says the cube has side lengths from that if this is my radius of my cylinder, then all the way across my circle, or all the way across an edge of my cube, is going to be 10. So S is 10. So the height of the cylinder is, if this whole thing is 22, and we've already used 10 up here for the height of the entire figure, then the height of the cylinder itself is 22 minus 10, or 12 feet. The volume of the cube then is going to be 10 cubed, or 1,000, and then the volume of the cylinder is big B times H, so 25 pi times 12, which is 942.5 cubic feet. And then all I'm going to do to get the composite is to add those two pieces together. So I get 1,000 plus 942.5 feet cubed, or 1,942.5 feet cubed. So go back and watch that little part of the video again if that didn't make sense, as far as kind of breaking down how all those dimensions relate to each other, before we go on and fill in for part B. But as we get to part B, we now have not oblique anymore, but we have definitely a composite figure, because we have a periscope here, just a rough one. Periscopes, as you know, are made up of tubes and mirrors basically, and so when you are looking as the person down, like in a submarine, this is the person looking into the mirror here, so that we can actually look here but see up the tube and then out the outside of the submarine, so we can basically kind of cheat and see how all of those reflections would come down to you. So the periscope is made up of 2 congruent cylinders and 2 congruent triangular prisms, each of which is a cube cut in half along one of its diagonals. So this right here plus this right here is going to equal 1 total cube. That's important to know. The height of each cylinder is 6 times the length of the radius. So that's important to know too. We're going to use the area of the base formula to begin with, where B equals pi r squared because it's a circle, and we're told that that is 36 pi. So pi r squared equals 36 pi, which gives that my r is 6. So if we calculate the height of each cylinder, since they are congruent cylinders, 6 times the radius, or 6 times 6, gives me that the height of the cylinder is 36 inches. And then the faces of the triangular prism that intersect the cylinders are congruent squares. And notice as we go across the circle that the diameter of the circle is one side of the square again. So that's going to be 2 times the radius, which I found, and that is going to be 12 inches for a side of the cube. So now the volume of the one cube with those two pieces put together is 12 cubed, or 1,728 inches cubed. Then we're going to find the volume of the two cylinders put together. So that's 2 times, here's my big B, area of the base, 36 pi, times the height is 36. And I should get that that is 2,592 pi inches cubed. And then for the composite, I'm just going to add those up and get the sum. So 1,728 inches cubed plus 2,592 pi, and then do some approximating on my calculator, and I get 9,871, and to the nearest tenth, as we were told, is actually 0.0 there, inches cubed. So those are some composite figures to get you guys started. I do want to talk through you. We don't have any actual measurements at the top of page 931 next. But we have this time a pipe consisting of 2 concentric cylinders with the inner cylinder hollowed out. Whenever you see that word hollowed, instead of adding, notice we're going to be subtracting the areas out. So we're just going to write down just a quick little formula here for how we would calculate the volume of this solid pipe. We're going to write a volume formula kind of, you know, just in terms of the shapes. So first we're going to take the volume of the big cone, or big cylinder, and we're going to subtract out the middle hollowed out cylinder, which is the volume of the small cylinder. Now if we put that in terms of the variables that were given here, we're going to take pi times the radius of the big cylinder, which you can see goes all the way out here, and they've labeled that as R1. So pi times R subscript 1, still squared, pi r squared is the area of the circle base, times the height. And then we'll do the same thing with a small cylinder, only this time on that diagram we're looking for the inside radius there, which is R2. So that's R subscript 2, still all squared, times H. And so that's what we would do if we had actual measurements for calculating this. But I just wanted to talk through a hollowed out example as well as a sum and put the two shapes together example. Okay? So we're going to go ahead and go on to our evaluate tomorrow. Just wanted to get you started on working through some of these videos, and we are actually going to start the evaluate the basic problems today. So you see that your homework or your practice for this section is broken into 2 days for each day of for each lesson, 18.1 through 18.4. Today we're going to start with day 1 of 18.1, and those should be pretty straightforward using area of the base, big B, times the height. And then the next day we'll go on and we'll do some more of those composites again. All right, thanks guys.